Hello, everybody. Welcome to, what are we, week 4 now? I don't know. I think it's at this point where we officially lose count. But I do know that this week we're going to be talking about regression. Go back and forth between, should I talk about a regression before ANOVA? I know in undergrad we tend to go t-test, then ANOVA, and then factorial ANOVA, and then circle back to correlation and then regression. And I think that at the graduate level, what I would prefer to do is go ahead and contextualize pretty much what we're going to be doing from here on out, except for when we get to the non-parametric stuff at the end. That's going to be at the end. In terms of something called the general linear model. So we're going to be focused on a linear model today, talking about regression, but I don't really, include correlation as part of this linear model. So I think that talking about correlation first, branching into regression, contextualizing with the linear model, is not a bad way to go. So we're going to go ahead and start off a little early in the semester talking about regression, and then we'll circle back to t-tests and ANOVAs next and build up to multiple regression in the second unit. But anyway, that was a really long introduction. So we're going to be talking about the linear model today in terms of regression. But when I say general linear model, which is why I have general there in brackets, what I'm saying is that the linear model can be applied to a lot of the tests that we do. Okay, so it's not just about regression. And sometimes it's easy to kind of think that it is. So today we're thinking in terms of the linear model for regression. And so the examples and stuff that we're going to be using today are going to be very regression specific. But we can apply this to t-tests, ANOVA, et cetera. And we're actually going to see some of the things that we can do in regression and the ways we can think about partitioning in regression towards the end of the lecture today. It's going to look really familiar if you remember anything from ANOVA in undergrad, which I think is actually kind of cool. And then today's lecture is going to be broken up into 2 different PowerPoint slides, 2 different presentations. So I want to spend this presentation really just talking about the concept of this linear model and the concept of regression, how it works. And then I do think that, because this is a very applied course, I want to step back and talk about the assumptions separately, because the assumptions as we work in the lab and all of that good stuff, we're going to need to be well acquainted with a lot of that. Some of them more than others, but anyway, so that'll be a separate slideshow. But all right, Dr. Prowl, let's get going. Okay. Oh, it'd be nice if there we go. All right. So, yeah, pretty much exactly what this says. This is what is a linear model, all right? So we're taking the value of one variable and we are predicting it from another variable. So we have this variable X, we want to predict Y. Based on X. So this is a hypothetical model, okay? It is a hypothetical model. The math that underlies this model is made up by mathematicians who are far more brilliant than I. It's a linear model. So there you go for redundancy, right? But what we're saying is that the relationship is described using the equation of a straight line for this linear model. Okay, so these are all very important. These are going to unfold as we go through this presentation. But I think the hypothetical part is important, right? As we don't always know every single aspect of the math that underlies some of the things that we talk about. That is for mathematicians. So here we go. All right, I do want to acquaint you with some of this terminology. A lot of this terminology is how you're going to see things on this slideshow, although there might be some slight variations. This is just to help if you run into confusion later, but I do want you to remember that different resources will have different ways of saying the same thing. So I recommend that when you see these symbols, and that's just not in this class, that is in any stats course you take in the future, if you see these symbols, really understand what they mean. And when you see the symbol, don't read it as X and Y. Try to make your brain flip that switch, right? To where your brain will actually circle back and say what it is. So Y is the dependent variable, X is the independent, also called the predictor. The predictor. Y on this chart also says criterion. So you'll hear criterion. You'll hear me use the word outcome a lot. It all means the same thing, but have that kind of as an automatic, automatic in your brain, so that, whenever you encounter literature, which you will, oh my goodness, you will, that uses different symbols, you're not going to be lost, because you're going to know that, oh, this is the independent variable. Oh, they're specifying it with this, although that's usually X. But anyway, there's always variations. Be ready for it. A lot of people let that trip them up more than is useful. So, okay. So for a linear model, we're talking about fitting a straight line. Okay, so this is just kind of a conceptual way of looking at this formula, both using words and then actually using symbols that you'll see more customarily. Okay, so whenever we're talking about the linear model, we're talking about we have these observed data, right? Or we have data that's comprised of model plus error, right? Data that we're interested in, right? Predicting. So with this formula, we can predict an outcome for a person. With this model, we can predict this outcome Y using this formula and some estimation methods. So when you see this, if you see B subscript 0, that's referring to the intercept, and that's the value of Y when X is 0. So it's the point of the regression line that crosses the Y axis or the ordinate when we're working with data. Okay, so you'll see the axes, and you'll see, I'm going to show you a slide in a second that'll say this, it'll show you a little bit better than how I'm saying this. So this gives us an idea of where the outcome variable, that Y, is actually centered. Okay, and also it's going to help us how, for some people like to think about how it helps you interpret the coefficient related to X too. But anyway, so you see here, you've got B subscript 1, B subscript 2. So X is just the variable, right? The variable X. Well, those B subscripts are the coefficients for the predictors, right? That's where we're getting like the gradient and the slope of the line. So it tells you about how steep is that slope. And then it also tells you what is the strength of that relationship, right? So B actually has a little bit of like a magnitude component built into it. Okay. So, oh, I wanted to say one more thing about that. So, whoa, that's the wrong way. Okay, all right. So this equation right here, don't get tripped up. Today we're talking about simple regression. So this equation is set up more for multiple regression and for if you're working with multiple predictors, right? That's the 1, 2, and then when you have the ... all the way to n, that's just saying for all of the different variables you have and all of the different coefficients you have, that's it. And then remember, E at the end is error. There's always error to account for, or that we can't account for. There's always error that we have to acknowledge, I guess would be a better way of saying that. Okay, and here's just the little illustration of predictors and slopes that I think is kind of useful. So as you can see, the intercept is where everybody's kind of jumping off. See how X is 0 right here? That's that point of Y when X is 0. So that's the intercept. And then you can see, so there's the same intercept and there's different slopes coming off of it. And then over here on the right, you have the different intercepts, but then the same slope. So the relationship's not really changing. It's just the starting point on the intercept that's changing. Okay, all right. So how can we think about this using a kind of realish world example? So I do like this musical example, okay? So, all right, so we're talking about a record company CEO wants to predict album sales from advertising, okay? So you've got 200 different album releases. So you've got your outcome variable is the actual sales, okay? And then your predictor variable, in this case, I should have that's just singular for this example, the amount of money spent promoting the album before release. So you've got X is the amount of money spent promoting the album before release. Y is the sales. That's what you're interested in predicting in this, in this linear equation here. Okay, so we want to predict how much we would sell based off of how much we would spend on advertising. Okay, so conceptually, there you go. There's a much simpler way of looking at simple regression. So we've just got the one X variable, right? We're going to need to figure out this coefficient. I'm not doing that yet. And then we've got the intercept and we've got Y. Okay, that's what we're interested in predicting. So you can break down, I guess, conceptually the formula like this. So you would say, okay, Y is album sales. And then so we need to know, of course, what the intercept is. And then that B coefficient, but it's that B coefficient times the advertising budget. And then you have to account for some error too, right? Or we just acknowledge that there's some error there. Well, pretend we know the value of the intercept to be 50 and the value of the coefficient to be 100. Now this is purely hypothetical. These are also expressed in thousands. That might be important for some of you when you're conceptualizing this. Okay, so say that we have that information. Okay, we have the information, we understand what the intercept is, we understand what the value of that coefficient is. Well, then what we can say is, okay, well, what I would really like to do is I would like to spend $5,000 on advertising. What can I expect with album sales if I spend $5,000 on advertising? So at that point, it's really just plug and play, okay? So whenever you do the math, it breaks down to, based on the model, we can predict that by spending $5,000 on advertising, we should be able to sell about 550 albums. So we also still know that there's error to account for, but now we have what's called a predicted value. Okay, we have a predicted value. That's what that is. So this is what this regression line is based off of, okay, this best fitting line, okay? We use this thing called the method of least squares. So if you look here, you see that the orange dots are the predicted value of the album sales from the previous example, and the blue dots are what we observe in the data. And then those dotted lines are the differences between what was observed and then what was predicted, right? So that's you'll hear it called the distance, the discrepancy, the deviation. It's all getting at the same thing, okay? So when we're talking about the method of least squares, right? That means that you take each of these error values and you square it. Okay, and that's, so think about that. That's just like what we talked about already. It maps right onto what we were talking about way back in the day in the first week, when we were reminding ourselves how we calculate deviations and variance and all that good stuff, where we had to look at that deviation and then square it, right? So you're doing something like that here. So those are the squares that we're talking about. It's a squared error term. And the regression line is going to run across the data in such a way that minimizes the squared error term as much as possible, okay? So the procedure minimizes the sum of squared errors between the actual scores of Y and then what we predict Y to be, okay? That's where that comes from. So remember, for the regression model now, we're talking about, when we say estimating the linear model, we're going to run through a bit more of this in terms of regression. So remember, we're talking about, for regression model, we're just talking about fitting a straight line, okay? So we're gonna use the least squares method that we just talked about, and we're gonna estimate the coefficient, and we're gonna estimate the intercept for that, okay? How on earth do we do that? Now, I want to make sure that everybody understands that this is not a class where I'm going to have you doing a bunch of hand calculations. I think it's important that when we can, we don't spend a lot of time on the formulas, right? This is not we're not math majors, right? But let's take a look. I mean, you want to know what's going on in there, because that tells you something about your data, and that'll, yeah, it really helps you understand, I guess, the mechanics a lot better. So let's pause and see how this works, okay? So this is taken from the Gravetter book. So I know some of you might have that based on my recommendation. I'm going to deviate a little bit from it, okay? But it says the same thing. Where the formulas I'm going to show you are going to say the same thing. So the formulas from Gravetter, the intercept is going to look a little bit different. I think that the B coefficient is pretty spot on. you know, the intercept is showing you it's the mean. That's what M is, the mean of Y minus the coefficient B times the mean of X. And then you get that coefficient B by taking the correlation coefficient, multiplying it by the standard deviation of Y divided by the standard deviation of X is what that says. Okay. So here's, I just wanted to touch base with a visual here that's actually showing you data, okay? And this is a tiny little data set, okay? This is a N of 5, okay? So you got 5 responses on both X and Y here. And so it's easy to calculate the mean, but you know, in case it helps looking at this, the mean of X is 3 and the mean of that Y is 9. And so what you see is, you see the columns of raw data for X. The raw data for X is 1, 2, 3, 4, 5. Raw data for Y is 5, 8, 8, 11, 13. And it looks like the graphic didn't come out quite the way it should. It should be X minus X bar and Y minus Y bar, okay? So you take every X response and subtract it from the mean, or subtracted the mean from the raw data, and you do the same thing for Y. And that's where the column of X minus X and Y minus Y comes from. It's actually raw X minus X mean, raw Y minus Y mean. This is all, I know, probably very familiar to a lot of you, okay? And summing up the squares of those, right? Remember, that's how we calculate the variance. That's what's going on over to the left. So we've already talked about this. And then we talked about last week, whenever we learned about correlation, we talked about how to get the covariance out of that, okay? So we're talking about the sum of cross products versus the sum of squares. And I believe the Grebetter book also has an example of how to calculate the B coefficient using the sum of cross products. If you're interested in that, go ahead and take a look at that. I'm just gonna show you the going from the correlation coefficient method here, okay? So to estimate that slope, we want to go after that B coefficient for that slope, okay? We're going to go after the correlation coefficient, okay? So, and that is the formula that we discussed last week. So remember, we just calculated the variance up here. Notice that that's squared, in case you're like, whoa, where'd the square root come from, Dr. Peratt? It's right there because we have to get that square back out of the variance to get it back to a standard deviation so that we can use it and we can interpret it. So that's where that came from. So we see a pretty large correlation coefficient going into this formula, which is an indication that your B is going to be big as well, right? Relatively speaking to your data. So 0.97. And then it's just plug and play. So then down at the bottom, you see, okay, well, there's correlation coefficient. I'm going to plug in, you know, the standard deviations for X and Y. Yeah, I'm not going to walk you through that. You can look at the formula. There it is. It works out. Okay. So we know that we have a B coefficient of 1.9 that we got from the correlation coefficient of 0.97 and all of that other wonderful information. Okay, so estimating the intercept, this is the exact same formula that Grebetter has. It's just using Y bar and X bar instead of the big mean. I want to say Grebetter also uses an A instead of a B underscore or a B subscript 0, I think. Anyway, still going after the intercept there, I believe. So it's just the value of Y when X is 0. So we're just getting rid of the X here, basically. Okay, that's pretty much it. Okay. And so now, because we've calculated the intercept and we've calculated our coefficient B, we now have a regression model. Of course, add plus error, right, would be probably the more appropriate if we're thinking in terms of the theoretical linear model, but at its most basic form, here we go. There's our regression model. Okay, so now that we have this model, we can now predict Y for any given value of X. That is the power of the regression model. So think about it back to the you know, advertising budget and the you know, record sales or album sales that you could plug anything in here for X, and then you could find out, okay, well, what do you predict? How much am I going to sell if I allocate $8,000 or $12,000? You can just do that all day. So it's really, it's useful in that way. But how do we tie it back to null hypothesis testing? I mean, we spent a lot of time a couple of weeks ago, you know, listening to me drone on about hypothesis testing, right? So the null is essentially saying if there's nothing to predict, then y is only a function of y, meaning that we can just use the mean itself to predict the outcome variable. Like there's no point in having any other variable, right? The mean of y is sufficient to predict y, okay? The alternative is essentially saying that there is something to predict and y can be predicted as a function of x, right? There's probably a lot of different ways that you can put language on that, but that's kind of how I tend to think about it. Okay, so we know that if we run some tests and we find a significant result, meaning that we've rejected the null hypothesis, that's something then we can think about this alternative model here, okay? All right, so let's think about the alternative model and the null model as far as what it actually looks like when we put the data on it, right? So if we can use y, all right, if we can use the raw score of y to predict y hat, which we've obtained because of the least squares method, then if that's true, okay, let's think about this just conceptually. And so I'm going to show you the column here, y minus y hat for each of them, right? If the null model is true, we should expect that discrepancy, that sums of squared errors, right? That discrepancy, we should expect it to be a lot smaller for the null model than the alternative model, because you're saying, no, there's a lot less error in this null model. We're pretty spot on with y already, predicting y hat, right? But as you can see with these data, you've got y minus y hat on the left for the null model. That's a 38, right? This the sums of the squared error there is 38. And then the alternative model, that's a 1.9. So you can see that the alternative model actually has a much smaller overall discrepancy, right? Or smaller discrepancy whenever you calculate the sums of squares there than the null model. So that's usually good. That's a good indication that we are probably going to reject the null hypothesis. It seems like this alternative model is kind of where it's at. We'll see. All right, so we do need to talk about effect size too, right? So we make this prediction using regression, and we're predicting y, we're predicting the outcome of y, and you know, we have what seems to be, you know, a pretty large coefficient for this, right? But, well, how good is our prediction in terms of magnitude? So you'll see that when we have two variables, r squared is the same thing as the coefficient of determination, okay? And so what we're doing here, I think I need to flip back and forth to make sure that you kind of make this connection here. I realize I might be speeding ahead too much. All right, so I'm going to slow down for a second. All right, so the effect size for regression, we're going to go after something called r squared, okay? Now, when you just have two variables, r squared is going to be the same thing as the coefficient of determination that we see in correlation. They should map onto each other, okay? Just regular r squared, not adjusted. We'll talk about adjusted in a second. So you see the formula for r squared is the sums of squares errors for the null hypothesis minus the sum of squared errors for the alternative hypothesis divided by the sum of squared errors for the null hypothesis. So notice that formula, that what you're really doing is you're just removing the null hypothesis, so you're only getting the effect for the sum of squared errors of the alternative hypothesis, okay? The null hypothesis is getting wiped out, okay? So 38 minus 1.9 over 38, let's go back, all right? So there's your 38, there's your 1.9, so there's your sum of squares for the null, sum of squares for alternative, divided by sum of squares for the null. That gives you an r squared of 0.95, okay? So if you multiply, if you take R from the correlation coefficient, which we already figured out, and then you square that, you should get 0.95 because this is just, we're just looking at X and Y here. So it's just a bivariate, just like what we were doing in correlation already. So it's pretty neat, okay? And so you can just kind of know pretty intuitively that that is a huge effect. So that's a really, really beautiful effect. Now, something that I want to pause really quick, and I don't want to just fly right past the sums of squares and talking about that. What the general linear model is looking at the relationship of a single independent variable and a single dependent variable. There are 3 types of sums of squares to think about, okay? These are going to be very important when we get to ANOVA. I'm sure many of you remember talking about sums of squares in ANOVA, but it also applies to regression because they're all housed under this general linear model, okay? So this is also going on under the hood with regression, although with regression, we tend to think more in terms of like that B coefficient, which we're gonna talk more about the significance test for that in a minute. All right, but the partitioning for the sums of squares applies here, so I wanna talk about it. So, so the sums of squares total, okay? Let me see if I can explain this. Okay, so if you look back here at this null model and you see the sums of squares equals 38. And basically it's just saying, hey, there's this discrepancy to account for. There's some kind of variability going on where Y is not predicting Y hat. There's a lot of variability in here that we're not accounting for, okay? That's why sums of squares is equal to 38 compared to the other. Now, whether or not your sums of squares is big is going to change. It's always going to be relative to the model that you're conducting. So I don't want you to get hung up on thinking, oh, 38 is a big sum of squares. It just depends. I told you that was going to happen a lot here, right? But what this 38 is saying when we see this Y minus Y hat is that there's just like this world essentially of variability that we need to account for. You know, this number 38 is like saying, here's like this whole piece of variability pie, right, that we need to account for. Okay, so we know that some of that may be due to the variability from X that overlaps with the variability on Y, right? There's variability from X that's contributing to this variability on Y. And so that's what this sums of squares 1.9, let me make sure I'm not saying this right. Hold on, I'm pausing. All right. All right, so it's due to the variability in X, but this is how does Y vary as a function of X? But we also know that some of that is chalked up to error that we're not accounting for. That's where I was going, okay? It's chalked up to error that we're not accounting for. So we're going to see this on a source table on our SPSS output, but we're going to hang out with it more when we cover our ANOVA unit, okay? So we've got this total sums of squares, and then we've got this sums of squares that's associated with the effect itself, okay? So that's the sums of squares between. Or we'll also see it as the sums of squares for the model, okay? And then you have the sums of squares that's associated with the error, okay? So that's where I was going at there. I don't want to get too caught up in deciphering, okay, here's the total, here's the error, here's the between, okay? But when you talk about the sums of squares for the model, that's the sums of squares that's associated with the effect that you're interested in. So that would be the effect of, you know, X in this case on Y, right? But then there's all this other stuff that you have to account for, okay, which can be kind of, that can be problematic, right? And so we know that sums of squares total is comprised of this variability that we can measure because of this effect that we are trying to measure. We're modeling accordingly. We're modeling specifically so that we can measure this effect. But then there's also this error that a lot of times we cannot account for. And so we have to account for all of that, okay? And that's how the sums of squares is partitioned. I don't want to spend too much time talking about that for regression because we're gonna really dive into that more for ANOVA. And I think it's a little bit easier to think about whenever we start talking about ANOVA. And I also don't want to throw too much at us collectively in this first week. So, but I did want to stop and just mention it. Let's just talk about it so that it's in your brain. So whenever we come back to it, it's not like, whoa, what is this? You know, it's not going to be totally new. All right, good. Glad I paused there for a second. Okay. Okay, so the last couple of slides here that I want to talk about for this portion of today's content is something called the standard error of estimate. Okay, so I mean, we can make predictions, you know, with our regression equation all day. You know, we can do that. We can be like, yeah, there we go, and there's my coefficient, and it's strong, and all that good stuff. Or it's okay, it's kind of moderate, it's kind of weak, you know. So we can make predictions. We can predict the extent that, you know, X maps onto the variability in Y, that we can use X to predict Y in that way. We can make predictions about the nature of the direction, right? So we didn't really talk about that a lot, but I guess I need to bring that up at some point, that, you know, whenever you have these regression coefficients, we interpret it kind of like R as far as the direction goes. So if it's positive, that means that as X increases, we can predict an increase in Y. And if it's negative, that means as X increases, we can predict a decrease in X. So I guess I probably needed to say that explicitly. So yeah, so we can make these predictions, but at the end of the day, without formalized hypothesis testing, we don't know if these predictions are accurate, right? Like we don't know, this is hypothesis testing. We are working with sample data. To what extent is our sample actually saying something meaningful in terms of the population, or to what extent is it really just some kind of error that we're finding, right? It's not really an actual effect that we can trust. Let me see. So then we need to talk about the standard error of estimate. So you can make predictions with the regression equation, but you need the standard error of estimate to tell if those predictions are significant. Can you significantly reject the null hypothesis? Okay. So the regression line, remember, is based off of, oh wait, I don't want to go. Oh no, not at the end of the slide here. Okay. So I guess I probably should have just read this part of the slide. All right, so when we're talking about the standard error of estimate, we're talking about the standard distance between the predicted Y values and the actual Y values on the regression line. So recall the method of least squares. Let me keep me in this pause. I get really excited and then I start rushing ahead. You just slow down. All right, so I'm going to show the slide that I already showed before, okay? No, not that one, this one. Okay, so remember that we're talking about, we're using this method of least squares to get this regression line, okay? And so there's going to be discrepancies from where data points actually are and where we're predicting them to be, okay? So this is how we calculate the standard error of the estimate, and that's going to go directly into our computations, not that we're going to be doing any of that by hand, but into our computations under the hood in SPSS to determine whether or not our finding is statistically significant, okay? So you've got the sums of squares for the residual. That's just that. See that it's sigma parentheses y minus y hat squared. That is exactly what is on this slide right here. Now, what we need to do is we need to obtain a measure of variance for this. Okay, so we're going to divide it by the degrees of freedom. That should look very familiar to things that we've already been doing. Okay, so in this case, degrees of freedom is going to be 2. We're gonna lose 2. So it's going to be whatever n is minus 2, because we have to account for both X and Y, okay? So each variable loses degree of freedom because we're estimating the distance from each of those variables' raw data scores to that predicted line, okay? And, you know, the mean is kind of included along the way in these calculations. And so because of that, we're going to lose a degree of freedom. There's a restriction placed on each of those, just like there was with correlation, okay? So it's going to be n minus 2 in the denominator, okay? And then so it breaks down to the formula for the standard error of estimate there. You've got the square root of the sums of squares for the residuals divided by the degrees of freedom, and that's it broken down a little bit more for you. Okay, so again, we're not computing this math, but just know that just like we've done before, we need to figure out, we need to get a general sense of what is an error term that we can use for our null hypothesis testing purposes. That's what we're using here, standard error of the estimate. Okay. All right, that is a lot. So I really encourage you to let yourself slow down, go back and listen, okay, and think through what I just talked about, okay? While I don't want to make these lectures so long that they're exhausting and that you lose your focus, I do want you to pause along the way and just kind of think about it. Let it marinate for a second and think about if you could, if I asked you to explain it to me or teach it to me, like how would you spit that back out to me? A lot of this will make more sense too as we go into our lab and we start seeing this output, and we'll start piecing this together a little bit more, but it's a lot to think about. So you might be thinking about, okay, well, so we talked about correlation, we talked about regression. Why am I not including correlation, you know, as part of this general linear model? Both of them are talking about a linear relationship between two or more variables, and they're highly related, right? Like remember we talked about the effect size of regression equals the square of the correlation coefficient when you're just talking about two variables. But the regression coefficient is the correlation coefficient, but it's adjusted. So it's adjusted by the scale of X and Y. Okay, so that's something to think about. Okay. One more point to make on this slide, on this slideshow, talking in terms of generalizability. So remember along the way, I try to remind you of this, you know, it's always kind of taking it back to why are we even here? Why are we doing any of this as far as statistics go? Why is this so important? And remember that what we're hoping to do is generalize the sample model to the entire population. Okay, if we're going to do this, we have to take into account some assumptions of the linear model that must be met. So I have those assumptions on another presentation that you should access whenever you can after this one, because violating these assumptions may stop us from being able to generalize to our target population. So it's kind of important to think about. But anyway, that is all I have for this. Please feel free to ask me any questions during office hour, or you know, if you want to you know, pop into the discussion board on Canvas or send me an email, although I do encourage the questions about content to go to the discussion board. Please feel free to do so. Hopefully some of this that seems maybe a little confusing right now, hopefully, you know, whenever we get on SPSS, we actually run the tests, hopefully it won't be quite as confusing as we talk through it with data in front of us. But anyway, that's all for now for this one. And I'll see you soon when we talk about assumptions.